Imagine you are standing on a highway, one road, but instead of a single lane, there are three identical lanes, all carrying traffic together. That is exactly how electric power prefers to travel in the real world. For reasons connected with economy, efficiency, and smooth operation, electric power is transmitted using a three-phase system. Instead of pushing all power through a single conductor, we divide the work into three identical phases, each sharing the load equally. Now here is the most interesting part. Even though power is flowing through three phases, each phase carries only 1/3 of the total power. So instead of making the system complicated, engineers do something very smart. They say, why not analyze just one phase, understand it completely, and then apply the same logic to the remaining two? That is exactly what we do. And before we go further, let me remind you, in my previous video, I explained the complete performance of a short transmission line, including voltage drop, regulation, and efficiency in a general sense. If those basics are still unclear, I strongly recommend watching that video first. It will make today's discussion much smoother and more enjoyable. On the screen, you can see a three-phase system supplying a balanced load. The generator is connected in star, the load is also connected in star, and each conductor has its own resistance and inductive reactance. Now, instead of staring at all three phases together, we mentally zoom into just one phase. Once we do that, the entire three-phase system suddenly looks like a single-phase circuit. This is why all the expressions we derived earlier for a single-phase short transmission line, such as voltage regulation and efficiency, can be directly applied to a three-phase system. But there is a small condition. Since we are analyzing only one phase, we must use phase values. That means the sending end voltage is the phase voltage, the receiving end voltage is the phase voltage, the resistance used is the resistance per phase, and the reactance used is the reactance per phase. Once this is done, the mathematics becomes familiar, friendly, and predictable. Now focus on what is happening inside that one phase. The conductor has resistance, which tries to oppose current like friction on a road. It also has inductive reactance, which behaves like inertia. It doesn't like changes in current. Current flows from the sending end, passes through resistance, then through inductive reactance, and finally reaches the receiving end load. Everything you see on the screen is nothing but a short transmission line represented per phase. This single-phase representation is not an approximation. It is a perfectly valid engineering model as long as the system is balanced. Let me ask you something. Why do you think engineers prefer balanced systems so much? What problems do you think arise if one phase starts behaving differently from the others? Tell me your thoughts in the comments. Now comes the real twist in the story. The performance of a transmission line does not depend only on resistance and reactance. It depends heavily on something called load power factor. Power factor decides whether current and voltage are walking together, or one of them is dragging its feet behind. And this power factor directly affects voltage regulation and efficiency. Let us talk about voltage regulation first. Voltage regulation tells us how much the receiving end voltage changes when the load is applied. For a short transmission line supplying a lagging power factor load, the percentage voltage regulation is expressed like this. Percentage voltage regulation equals I multiplied by R multiplied by cos of the receiving end power factor angle plus I multiplied by XL multiplied by sine of the receiving end power factor angle, and this entire quantity is divided by the receiving end voltage, then multiplied by 100. Now notice something important. For a leading power factor load, the expression almost looks the same, but with one crucial change. Instead of plus, we have minus. So it becomes percentage voltage regulation equals I multiplied by R multiplied by cos of the receiving end power factor angle minus I multiplied by XL multiplied by sine of the receiving end power factor angle divided by receiving end voltage multiplied by 100. This single sign change completely alters the behavior of the line. From these expressions, some powerful conclusions emerge. If the load power factor is lagging, or unity, or slightly leading, such that I multiplied by R multiplied by cos phi R is greater than I multiplied by XL multiplied by sine phi R, then voltage regulation becomes positive. Positive regulation means the receiving end voltage is less than the sending end voltage. Now think about this. For the same receiving end voltage and same power, if power factor decreases in a lagging load, current increases. Higher current means higher voltage drop, so voltage regulation increases. But if the power factor becomes leading and so strong that I multiplied by XL multiplied by sine phi R becomes greater than I multiplied by R multiplied by cos phi R, then voltage regulation becomes negative. Negative regulation means something very interesting. The receiving end voltage actually becomes higher than the sending end voltage. Have you ever wondered why capacitive loads sometimes increase voltage instead of dropping it? This is the reason. Which type of load do you think is more dangerous for insulation, lagging or leading? Comment your opinion. Now, let us talk about efficiency. Power delivered to the load depends on voltage, current, and power factor. For a single-phase line, power equals receiving end voltage multiplied by current multiplied by cos of the power factor angle. So current becomes power divided by receiving end voltage multiplied by cos of the power factor angle. For a three-phase line, total power becomes 3 multiplied by receiving end phase voltage multiplied by current multiplied by cos of the power factor angle. Again, current becomes power divided by 3 multiplied by receiving end phase voltage multiplied by cos of the power factor angle. Now observe the most important insight. For a fixed power and fixed receiving end voltage, current is inversely proportional to power factor. So when power factor decreases, current increases. Higher current means higher line losses. Higher losses mean lower efficiency. This is why utilities hate low power factor. It silently wastes energy like leakage from a cracked pipe. On the screen, you can see a power factor meter and a power factor regulator. These are not just laboratory instruments. They are installed in real substations and industries to prevent poor system performance. Maintaining good power factor is not optional. It is a necessity for stable voltage, reduced losses, and efficient power transmission. If power factor correction devices were suddenly removed from industries, what do you think would happen to transmission lines and generators? Share your thoughts. Now let me give you a real engineering challenge. An overhead three-phase transmission line delivers 5,000 kilowatts at 22 kilovolts with a power factor of 0.8 lagging. The resistance of each conductor is 4 ohms and the reactance of each conductor is 6 ohms. Now here is my question to you. What is the numerical value of the sending end voltage in kilovolts? What is the value of percentage regulation? And what is the percentage transmission efficiency of this line? I am not going to solve this. This one is for you. Try it yourself and write your final answers in the comments. Let us see how many true electrology engineers are watching. If this explanation helped you truly understand three-phase short transmission lines, please like this video. It tells YouTube that serious engineering content matters. Share it with your friends who struggle with power systems. And subscribe to Electrology if you want deep, textbook-level explanations explained like real stories. Also, you will see a join button and a thanks button below this video. Your support through these buttons directly helps me invest more time, better visuals, and higher quality content for this channel. Engineering education needs support to survive, and every contribution matters. I'll see you in the next video.